Okay, welcome to this short video on the composition of the Earth. As we discuss the composition of the Earth, it's important to remember that the Earth initially formed by the accumulation of millions and millions of meteorites, big and small. And so that's what this picture is illustrating, the bombardment of the Earth by all these meteorites. And again, I want to emphasize that the Earth is really just the product of all these bombardments. If all these meteorites hadn't crashed together and congealed together, there would be no Earth. One of the important consequences of this bombardment by these meteorites is that the early Earth was very hot. It was so hot, in fact, that the Earth itself was just this very thick soup of elements. It hadn't congealed, it hadn't hardened. You can think of the Earth at this time as just like a big ball of magma. The other consequence of this bombardment is that the chemical elements that make up the Earth really are just reflecting the chemical elements that made up these meteorites during this period of bombardment. So with that in mind, let's take a look at what the Earth is composed of and how it's structured. So this is a picture of the early Earth, and I just want to emphasize this point that all these meteorites crashing together is what formed our planet. So we have all these meteorites coming together during the early moments of our solar system, like that, and forming our planet. And so this is the thick, hot soup of elements that was the early Earth. So let's take a bigger view. Sorry, it's kind of a lopsided planet, but this is planet Earth. And if we look at the main elements that form our planet, we have oxygen, silicon, aluminum, sodium, which is represented by the letters Na, calcium, that's just Ca, potassium, K, and then we have iron, which is Fe, and magnesium, which is Mg. So our entire planet is mostly composed of this list of 8 elements. Now imagine again, this was the early Earth. This is a thick, hot soup. It's a big ball of magma. And as in like just a bowl of soup, you have the heaviest stuff sinking to the bottom, right? So if you have potatoes in a soup, the potatoes sink to the bottom and kind of the light stuff rises up to the top. Same thing with the early Earth. So the heavy elements, iron and magnesium, sank to the middle. And the light elements, like oxygen and silicon, rose up to the top. Now, one of the interesting consequences of this differentiation according to weight is that when this early kind of thick hot soup finally congealed, when it finally hardened, the differentiation according to weight of these elements created different layers in our planet. So let's take a look at those different layers. So here's the Earth, I'm making it small for now. And what we're going to do is we're going to take a wedge out of the Earth, basically like a big pizza slice. Okay, so let's blow up that pizza slice. Like that. And we're going to start here at the middle, basically the middle of the Earth. And so the distance here from the surface is 6,000 kilometers. So this will give us a sense of scale as we move up towards the surface. And then just so you know where we're going, this is 0 up here. So the radius of the Earth is about 6,000 kilometers. If we start at the center of the Earth and we move up 1,000 kilometers, that's essentially where the inner core lives. So this is this inner part of the planet, and the inner part of this wedge is the inner core. Remember that this differentiation happened because the heaviest elements sank to the bottom and the lightest elements sank to the top. So the inner core, this is all the heavy stuff, so it's composed of solid iron with some nickel. An important characteristic of the inner core is that it's very hot. And it's hot for two reasons. So the first reason is that this is just leftover residual heat from when the Earth initially formed. You can imagine that any heat down here is going to have, well, you can imagine that it's taking a long time here for the inner core to cool down because that heat has to dissipate through essentially the rest of the Earth. So some of this heat is just residual heat from when our planet formed. And the other source of heat is from radioactive decay. These are radioactive elements in the inner core that are undergoing decay, and as a result, heat is generated. So you can think of the inner core as essentially a really, really big nuclear reactor giving off heat. The next big boundary happens at 3,000 kilometers. And this is the outer core. The outer core is also composed of iron and nickel, but the big difference here is that the iron is molten, meaning that it's liquid. Now, one of the interesting consequences of this molten liquid iron, it doesn't just sit there, it actually rotates. If we were to look at our planet from, say, outer space, and we're just staring down say along the axis of the North Pole, we would see the Earth rotating, 24 hours a day. It does a full rotation every 24 hours. So you'd see the sun, you'd see the moon rotate. I mean, the Earth. If you could look within the Earth and see these different layers, so there's the inner core is this small circle. The boundary of the outer core is this larger circle. If you could peer in, you would see that this liquid iron is also spinning. Okay, so the outer core is actually rotating. One of the consequences of this rotation is that it forms a magnetic field around our planet. So this dashed circle is the magnetic field. Now it turns out that this magnetic field is extremely important. Extremely important to us and to life on Earth, because what it does is it shields us from cosmic rays. So cosmic rays are constantly trying to bombard our planet. And this magnetic field prevents those cosmic rays from actually reaching us, which is a good thing because these cosmic rays cause a lot of DNA damage. And so if these cosmic rays were able to penetrate this magnetic field and reach us, they would cause DNA damage within our bodies, and that would lead to all sorts of nasty mutations, which of course we don't want. Now, another interesting characteristic of this magnetic field is that some animals can actually sense it. So, for example, homing pigeons can sense the magnetic field, and dogs can as well. So, if you've ever seen a dog circle around a bunch before lying down or before going poop, the reason why it's doing that is because it's trying to align itself with the magnetic field. Why it needs to do that, nobody knows, but it turns out that dogs also sense this magnetic field. Okay, so that is the outer core. And then the next layer takes us to right about 20 kilometers from the surface. And this layer is the mantle. Now, the interesting characteristic of the mantle is that it's not quite liquid and it's not quite solid either. In fact, it's kind of like silly putty in terms of its consistency. Because it's not quite a solid, and it's got kind of these liquidy, silly putty properties, the mantle actually has currents in it. So this is the mantle. With these currents, just kind of, this is just the mantle kind of spinning around like that. And as we'll see in a later later in the semester, it's these mantle currents that actually drag this upper layer, which is the crust. So before we move on to the crust, I just want to point out that the mantle is composed primarily of iron and magnesium. And even though I've drawn it to make it look like that's the composition of silly putty, um, that's actually the mantle. Okay, so the top layer of the Earth is the crust. This is the upper 20 kilometers. So when you look out the window, what you see is the crust. It's dominated by the lightest elements. So oxygen is something like 40%. Silicon is about 28%. So when you pick up a rock, it's mostly oxygen and silicon. And then the other light elements, aluminum, calcium, sodium, and potassium. But it's mostly oxygen and silicon. So again, this is all the stuff that floated up to the top. So one of the kind of corny jokes in geology is that we're essentially living on the scum of the earth. So this is all the stuff that floated up to the top during this early Earth, during the period of the early Earth. Oops. Now the crust has two components. There's continental crust and oceanic crust. And these two types of crust are just differentiated on the basis of their chemical composition. So the oceanic crust has a little bit more heavier elements than the continental crust, and so as a result, the oceanic crust just sits a little lower than the continental crust. And of course, water always tries to go to the lowest spot, and so the water that goes to goes to where the oceanic crust is, and that's why we have oceans, because that's crust that's just a little bit heavier, and that's where the water has collected. Okay, so this was just a brief introduction to the different layers of our planet.